There are basically two different technologies that are used for mixture separations. In pressure swing adsorption units, the MOFs and zeolite adsorbents are packed in fixed beds. In such cases, the separations are usually based on the mixture adsorption equilibrium. The intracrystalline diffusion of gas molecules usually tends to decrease the separation performance, and in some cases, the intracrystalline diffusion effects may be used to reverse the adsorption hierarchy. Such selectivity reversals are used to separate nitrogen from methane for producing natural gas to meet pipeline specifications, or to separate nitrogen from oxygen. In another kind of technology, we use the microporous crystalline adsorbents in the form of thin layers, typically of thickness of about 50 micrometers, and the mixture separation is effected by permeating the mixture across the membrane. The membrane permeation selectivity is a product of the diffusion selectivity and the adsorption selectivity. Diffusion is always important in addition to adsorption. These separations can be either driven by mixture adsorption equilibrium or by differences in the diffusivities of gas molecules. The ideal choice of a material for use in membrane constructs would be materials which allow the diffusion selectivity to enhance the adsorption selectivity. We now examine how to predict the mixture adsorption equilibrium from data on unary isotherms. Let's follow the derivation of the Langmuir isotherm. Langmuir got the Nobel Prize in 1932. We consider a checkerboard consisting of m sites. Let's assume that a fraction theta of the sites is occupied by the gas molecules indicated in red, and therefore 1 minus theta, which is the fractional vacancy, the rate of adsorption is proportional to the number of vacant sites, m times theta v times the fugacity of the gas component in the gas phase, indicated by F. We could also use the partial pressure, times the rate constant K adds. The rate of desorption is proportional to the number of occupied sites, which is m times theta. And the constant of proportionality is K des. We consider equilibrium between the bulk gas and the adsorbate molecules and equate the rate of adsorption to the rate of desorption, and obtain the following expression: K adsorption divided by K desorption times the fugacity is equal to the ratio of the occupancy to the vacancy. The ratio of the adsorption rate constant to the desorption rate constant is denoted by B, and B is a measure of the binding strength of the molecules. And the binding strength is related to the binding energy W. The occupancy is the molar loading of the adsorbent, say in moles per kilogram, divided by the saturation capacity, Qsat. The fractional occupancy can be derived in the form B times F divided by 1 plus BF. This is the classic Langmuir form of the unary isotherm. Let us consider the adsorption of a mixture consisting of components 1 and 2. Component 1 is indicated in red here. Component 2 indicated in blue. We assume that components 1 and 2 have equal saturation capacities, and each of these guest molecules occupy one site on the checkerboard that contains a total of m sites. We can write the expressions for the rates of adsorption and desorption of component 1. The rate of adsorption of component 1 is proportional to the number of vacant sites that are available, which is the total number of sites times the fractional vacancy. And the fractional vacancy is 1 minus theta 1 minus theta 2. The rate of desorption of component 1 is proportional to the number of sites occupied by the red guests, that is the fractional occupancy theta 1. Equating the rates of adsorption and desorption, we can derive the following expression relating the partial fugacity of component 1 in the bulk gas phase with the occupancies, fractional occupancies of components 1 and 2. B1 is the binding constant for component 1. This equals the binding constant that was derived in the previous slide for the unary isotherm. Analogously, we obtained an expression for relating the occupancy of component 2 on the checkerboard to the partial fugacity of component 2 in the bulk gas mixture. B2 is the binding constant for component 2, and this corresponds to the binding constant defined by the unary isotherm. It's now a matter of simple algebraic manipulation to obtain an expression for the component loadings in the mixture. We add these two terms and obtain an expression for the vacancy. The vacancy 1 minus theta 1 minus theta 2 is 1 divided by 1 plus B1F1 plus B2F2, and we can obtain an expression for the fractional occupancy of component 1 as the molar loading of component 1 divided by the saturation capacity equals B1F1 divided by 1 plus B1F1 plus B2F2. Similarly, the fractional occupancy of component 2 is the molar loading of component 2 divided by the saturation capacity. This equals B2F2 divided by 1 plus B1F1 plus B2F2. We define the adsorption selectivity as the ratio of the component loadings of 1 with respect to 2 divided by the ratio of the partial fugacities of components 1 to that of component 2. And it is easy to derive that the adsorption selectivity is simply the ratio of the corresponding binding constants, B1 divided by B2. The adsorption selectivity in this derivation is found to be independent of the bulk fluid mixture composition and the bulk fluid phase fugacity, which is F1 plus F2. For adsorption of a binary mixture of components 1 and 2 with equal saturation capacities Qsat, we can derive an expression for the entropy using the Boltzmann equation, S equals KLN W, that is engraved on his tombstone in Vienna. W is the Wahrscheinlichkeit, and for a checkerboard, we can calculate the value of S, and the following expression can be derived. The maximum entropy occurs at equal occupancies of each of the components. In other words, if the saturation capacities are the same, the entropy maximization principle suggests that there is no entropic preference to either component 1 or component 2. And the adsorption selectivity is dictated solely by binding strengths and not on the basis of entropic considerations. We'll find this discussion useful later when we consider adsorption of components with different saturation capacities. Let us illustrate the application of the binary Langmuir model that was derived earlier. We consider the adsorption of xylene isomers in AFI zeolite that consists of 1D channels with dimensions 7.3 angstrom at this point and 8.4 angstrom from groove to groove. Orthoxylene is different from the other isomers because it can align itself nicely face to face in these grooves, and has a higher saturation capacity than the meta isomer and the para isomer. Let's first consider a mixture of metaxylene and paraxylene. The unary isotherms are shown in red for paraxylene and in blue for metaxylene. The saturation capacities are approximately equal, and the binding constant for paraxylene is higher than the binding constant for metaxylene. Measurements of the isosteric heats of adsorption, that is an indication of the binding energies, are shown here as a function of the loading, and we see the isosteric heat of adsorption of paraxylene is higher than that of metaxylene, and this corresponds to the data on the unary isotherms. For a binary mixture of metaxylene and paraxylene, we can use the binary Langmuir model to calculate the component loadings of paraxylene and metaxylene and the adsorption selectivity of paraxylene with respect to metaxylene for a mixture of bulk phase mixture in which the partial fugacities of components 1 and 2 are equal to each other. The adsorption selectivity is constant and has a value of 2.6 and is independent of the total bulk fluid phase fugacity. An important assumption made in the derivation of the binary Langmuir model is that the saturation capacities of components 1 and 2 are equal to each other. This requirement is difficult to meet in practice, as illustrated in this graph that shows the unary isotherms for a variety of gaseous molecules in MFI zeolite. MFI stands for mobile 5, and it has a intersecting channel structure with straight channels and zigzag channels. Linear molecules can align themselves easily along either the straight channels or the zigzag channels. We note that the hierarchy of saturation capacities is hydrogen, the highest, with a saturation capacity of about 30 molecules per unit cell. The next is carbon dioxide. Then we have methane, nitrogen, ethane, and propane. The longer the chain length, the lower the value of the saturation loading. Here's a snapshot showing the location of molecules of CO2 and CH4 within the intersecting channels of MFI zeolite. This graph shows the adsorption selectivity for a variety of mixtures as a function of pore occupancy, and the selectivities were determined from configurational bias Monte Carlo simulations. In all cases, except this one, the adsorption selectivity is found to either decrease or increase with pore occupancy. This is the total occupancy of components 1 and 2 within the MFI framework. Let's examine the data for 50-50 mixtures of propane and methane. The selectivity is constant for a range of occupancies, and beyond an occupancy of 0.6 decreases by about an order of magnitude. And we note that the propane saturation capacity is about 12, whereas the saturation capacity of methane is about 20. So the data show that the adsorption selectivity decreases in favor of the component with the lower saturation capacity as the occupancy increases. The same is true for mixtures of carbon dioxide and hydrogen. Here are molecular simulations for 1585 CO2 hydrogen mixtures. For low occupancies below about 0.4, the selectivity is practically constant, but as the occupancy increases beyond 0.6, the selectivity is increasingly in favor of hydrogen that has a higher saturation capacity. For a mixture of CO2 and nitrogen, the selectivity appears to increase slightly with poor occupancies. And we note that the CO2 saturation capacity is higher than that of nitrogen. So there is a slight increase in the saturation capacity, and this increase is in favor of CO2 that has a higher saturation loading. For a 50-50 mixture of methane and nitrogen, the adsorption selectivity is practically independent of pore occupancy, and we note that the saturation capacity of methane is approximately the same as that for nitrogen. Finally, we have a mixture of CO2 and methane where the selectivity increases in favor of CO2 that has the higher saturation capacity. So two messages emerge from these data, that the adsorption selectivity is dependent on the pore occupancy and appears also to depend on the differences in the saturation capacity of the guest constituents.